Hello, everyone. In this session, we will be talking about simplifying capacity management of EC2 instances using autoscaling. Now, this is a very interesting topic since there are multiple dimensions to the elasticity that the AWS cloud offers. One of them being the ability to provision hundreds and thousands of instances in no time without any upfront capital expenditure. Another dimension is the one that we will be talking about in this session, which is around automatically provisioning and managing your EC2 instances without giving you a completely hands-off experience. My name is Anup Kapoor. I'm the Senior Product Manager for the Autoscaling service, and my goal is to help customers maximize their application performance while lowering costs. Now, at times, there's a misconception that EC2 autoscaling is just about adding or removing capacity as and when the traffic to your application changes. But that's not quite true. There's a lot more to it than that. We have customers who manage 100% of their EC2 instances using EC2 autoscaling. So I'm going to go over the 4 popular use cases that EC2 autoscaling solves for our customers. And then throughout, I will be highlighting several new features and capabilities that we've recently launched. And then we'll hear from Netflix how they are using autoscaling. So just wanted to mention real quick, this is a very special year for us. We are celebrating EC2 autoscaling's 10th birthday. And for the last 10 years, EC2 autoscaling has been standing by its customers and been letting them have better sleeps by doing the heavy lifting of capacity management on their behalf. So the first use case, automating the provisioning of instances. Now, when you use EC2 autoscaling, you will be hearing the term autoscaling group or ASG a lot, and you will be using it a lot. So an ASG is a logical group of instances. So say, for example, you have a collection of instances which is running the front end of your website. All those instances will be a part of one single autoscaling group. The ASG is bound by the maximum and minimum capacity. So the ASG is not going to go above the max. So you don't have to worry about cost overruns or runaway scaling. And similarly, it will not go below the minimum either. And then desired is what determines what are the number of instances that should be running in the ASG at any given time. So ASG will either launch instances or terminate instances so as to meet the desired capacity. Now the question becomes is, what are the properties of the instances going to be that are launched in this ASG? So that's defined by the launch template that you associate with the ASG. The launch template has all the properties, for example, what instance type should launch, a C5 large, an M5 large. What is the machine image it should launch with? If you're using golden images where you're baking all the software in a custom AMI, this is where you end up specifying the custom AMI as well. Now, if you're an existing autoscaling customer, you must be wondering, why is he talking about just launch templates and what happened to launch configurations? So launch templates are an EC2 construct, which were launched back in 2017, and launch configurations are an EC2 autoscaling construct. You can think of launch templates as very similar to launch configs, but being on steroids. They can be versioned. They've got support for all the latest EC2 features like T2 Unlimited, EBS tagging. And what we're seeing is a number of features that I'll be talking about today that we've introduced. They are available when you're using launch templates. So moving forward, launch templates are the way to go. So would highly encourage migrating to them. So once you have this configured, once you have the ASG and the launch template, that forms the blueprint. And then from there on, everything is automated. ASG is also fully integrated with elastic load balancing with all 3 classic load balancer, application load balancer, and network load balancer. So whenever an instance comes up, it will automatically get registered behind the load balancer. And then when the instance has to be terminated, it will end up draining the instance and then deregistering as well before the termination. Now, yesterday, we were very excited to launch the support, autoscaling support for dedicated host. Several of you might be already using dedicated host. So dedicated host, they have a very popular use case when you're bringing your own license to AWS. And essentially, you need access to the whole box because of your license obligations. So we are doing this through AWS License Manager. And we've introduced this new construct, which is the host resource group. So the host resource group is a collection of dedicated hosts. It's pretty dry in Vegas. So it's a collection of dedicated hosts, and you create a host resource group, and then you end up allocating some settings, for example, what the host allocation policy is going to be, the host release policy is going to be, what should happen if a dedicated host fails, the auto recovery functionality of it. So once you've configured this host resource group, this is what you end up specifying in the launch template as well. What else does this capability come with? Now you can launch, if you're using Nitro instances, you can launch multiple instance sizes within the same family on the same dedicated host. With the automatic allocation and release of hosts, you can better utilize your savings plans as well. And you can do cross-account sharing. So you can have one common dedicated host pool for all your organizations. So the intent of these features is that you be able to better utilize your infrastructure, your dedicated hosts, and in turn and even your licenses, and then in turn be able to lower your costs. So let's just take a look at a quick example how this works. So say you have an ASG which has to launch a C5 extra large instance. Now to begin with, there is no dedicated host available. So it ends up automatically allocating a host, and then will end up launching the instance on it. Now say another ASG comes in, it's got to launch a 2XL instance. So now it sees that the dedicated host is already available. It's got capacity to launch a 2XL instance. And once again, note that the same dedicated host can launch the extra large and 2XL instance on it. So that gets launched. And that's how all the subsequent launches will work as well. When the terminations have to happen, so say the M5 4XL has to terminate, that goes away. When the M5 extra large has to go away. After that, the dedicated host is completely empty, not required. It will automatically end up getting deallocated and released. So that was auto-scaling for dedicated hosts. Now, another very exciting feature that we just launched a few weeks ago was the ability to automatically recycle instances at a regular cadence. So all you've got to do is specify the max instance lifetime parameter in the ASG. And then ASG is going to do the heavy lifting of doing the replacements of the instances before they hit that time. So you don't have to worry about too many replacements going on at the same time, because ASG is going to end up spreading them out. You may want to do this for security reasons, for compliance reasons. But when we launched this a couple of weeks ago, I saw a lot of customers, they were talking on different forums about this functionality. And there was one common theme of excitement, which was that this is the solution to the problem of memory leaks. So I hope several of you can relate to that as well. If anyone was wondering what the magic number 604-800 is, it's just 7 days and seconds. So now that you have the capacity provisioned, the next is, how do I reduce the paging frequency? And what that means is, if anything were to go wrong with my EC2 instances, how do I let auto remediation happen? That means go cure my instances without any manual intervention. So ASG is integrated with both EC2 health checks and ELB health checks. If ASG detects that anything has gone wrong with the instance, if the health check has failed, it automatically detects that and then is automatically able to replace it. That's why we see that customers who are launching even one instance, they will end up placing that in an ASG and let it be managed by an ASG for this functionality alone. Now, from an AWS well-architected perspective, one of the best practices is to have your EC2 capacity across multiple AZs. And the reason is, if anything were to go wrong with one of the AZs, you still have capacity in the alternative AZ. So ASG does that for you by balancing the capacity across AZs. So in this case, if you've got 6 instances, it will launch 3 instances in one AZ and the other 3 in the other AZ. And if anything were to go wrong with any of the AZs, it detects that and is able to automatically retarget your capacity to the healthy AZ. And once it's done that, it continues to poke the constrained AZ. And as soon as a launch in that AZ is successful, it will once again end up rebalancing the capacity across the AZs that you've specified. The third use case is around making it super simple and easy to use spot instances. What are spot instances? Spot instances are EC2 spare capacity, which are available at a very discounted price, up to 90% off of on-demand prices. The infrastructure, the platform, the performance, everything is identical to an on-demand instance. The one difference being that if we need that capacity back for on-demand usage, we will give a 2-minute notification and we'll take the instance back. But with auto-scaling groups, they having the capability of being able to provision multiple instance types across multiple purchase options, that's what makes it super ideal to manage your spot instances as well. So all you've got to do is 3 things. You select the instance types that work for you. You select the spot allocation strategy. You can tell ASG, okay, just go and launch instances in the pool which are the cheapest. Or you can use the newly launched capacity optimized strategy, which makes the most efficient use of our spare capacity. It looks at the real-time capacity data. It's able to make predictions on the availability of the pools. And then it will accordingly end up placing it will make the launches on those pools. And the idea being that that should reduce the interruptions that you face. And then the last thing is you specify the percentage split between the on-demand and the spot portions. A couple of weeks ago, we also introduced the capability of assigning instance weights to the instance types that work for you. So in this example, you can see that I've assigned the weight to be the same as the number of vCPUs that the instance types have. So essentially, instead of the ASG now requesting capacity in terms of instances, it's going to be requesting capacity in terms of cores. So this gives you even more flexibility to be flexible across different instance types. So this is what the JSON for the mixed instances policy looks like. The 2 very interesting things to note here are the 2 parameters, the on-demand base capacity and on-demand percentage above base. This is what defines the split between the on-demand and the spot portions. So these 2 parameters, they give you a lot of flexibility. If you need 100% spot instances, you can do that. If you want 100% on-demand instances, you can do that. Why would you want to do that? Just to have backup instances. For example, if an instance type was not available, you still will be able to launch a backup instance type. If you want to just have a percentage split between the 2, you can do that. So what I've seen customers do is they'll start with, when they are just starting out with spot instances, they will set this as 5% spot instances. And as they get more comfortable with spot and as they understand that better, they'll just end up increasing this number. And if you just want to define a base on-demand capacity and then you want to turbo boost your application with spot instances, you can do that as well. We do have a Chalk Talk coming up for this on Thursday, so we will be doing a deep dive on this session. And then I do have some $50 spot credits. If you want to try it out, I'm more than happy to share that. Now, the last use case I want to talk about is the ability to automatically scale out and scale in your infrastructure as the load to your application changes. So what that means is I don't want to provision for peak capacity at all times for adequate application performance. I don't want to be paying extra when I don't need that capacity. I don't want my application to have sluggish behavior because of having not enough capacity. So this all goes back to the concept of the minimum, maximum, and desired that we talked about earlier. So the question becomes is that what should these values be set to and how should they be set? So the easiest way of doing this is by just doing manual scaling. You just go into the console or the CLI API, and you just update one of these parameters, and then ASG is just going to conform to the new settings. The second is schedule scaling. If you do have predictable patterns where you want to have capacity like 9 a.m. to 5 p.m., and then you want to shrink the capacity during evening and nighttime, then you can do that with schedule scaling. There's full support for cron expressions, so you can build whatever you want. The third is dynamic scaling with target tracking. So this works just like a thermostat or a cruise control in your car. All you've got to do is pick the metric that you want to scale on, for example, the average CPU utilization, and you set the target for the metric. So say you know that the application works well when the threshold is around 50% CPU utilization. That's what you set the target at. And then from there, target tracking does all the work. So you've got traffic coming into your application. The target is at 50%. If more traffic starts to come in, the CPU utilization on the instances is going to go up. Say it rises to 75%. From there, target tracking is able to calculate that, yes, I need another 5 instances in this case to be able to bring the CPU utilization back down. So it ends up launching the 5 instances. Once again, everything is happy, and everything's good to go. So what we see is that for the most part, target tracking works extremely well. But if for any reason you do need finer grained control of your scaling policies, you want to set your own alarm thresholds, you want to set your own steps, for example, add 2 instances when the alarm reaches 60%, add 4 instances when it reaches 70%. If you do want to have that granular control, you're more than welcome to use step scaling policies as well. And the last is predictive scaling. So with target tracking, what we saw was that it responds to the changes in traffic. So once the changes happen, then it provisions capacity. But we've got customers who say that we want to pre-provision the capacity. There could be 2 reasons. One is that they just have predictable patterns, and they want to pre-provision the capacity. The other is that the bootstrapping times could be longer. And for that reason, they just need to do it quicker. So with predictive scaling, it takes a look at the data of your application for the last 2 weeks, and then based on that, it ends up predicting the next 48 hours of the traffic. And then it can run a regression model on it and understand how much capacity would be required in order to cater to that traffic. And once that's done, it just ends up setting up schedule scaling actions, and that's how the capacity is provisioned. And this works extremely well with target tracking, because what predictive scaling does is it just ends up setting a baseline, and then target tracking can go and fill all the gaps and valleys and all the fine-tuning above that. With that, I would now love Netflix to come and share with us how they operate at the scale at which they do using auto-scaling.
No.
Can you hear me now? Okay, sorry about that. All right, thanks for coming. I know it's the last session. I'm the one who's standing between you and your dinner. I'll try, I try make your time worth it. All right, so for the purposes of this session, I think the most relevant number here is 250,000 reserved instances across 3 regions and across over 20,000 ASGs. That's the global Netflix footprint. So, well, obviously, it takes some effort to manage this capacity. How do we do this? With some help from AWS auto-scaling. Let's go through some features that we use, and later we talk about dynamic scaling. We do a deeper dive on dynamic scaling. It all starts with provisioning. And in terms of provisioning, AWS provides plenty of options. We can choose from bootstrapping options and rebalancing, health checks, instance termination protection. There's plenty of other options. But more importantly, AWS provides us with plenty of integration points so that we can build the next layer of abstraction on the top of it, which is our continuous delivery with Spinnaker. Spinnaker is an open source tool. It was developed primarily by Netflix. We run it in our environment. You can get it as well. You can get it on GitHub, install it. Spinnaker provides a higher level abstractions. For example, in terms of ASG management, Spinnaker has an atomic clone operation. You can get a deep clone of ASG with all the security groups and scaling policies and everything, all the metadata and everything that belongs to an ASG. Based on this, we can build pipelines and automate our delivery process from the pull request to testing, canarying, and finally deploying it in prod. And that allows us to build what we call an immutable infrastructure. Most of our, well, all of our mid-tier services, with very few exceptions, we're bootstrapping them with pre-baked golden AMI. We do not patch them. We do not change software throughout the whole lifetime of ASG. When the time comes to deploy a new version of software, we do Redblack deploys, which means that we spin up a new ASG with a new AMI that has a new version of software. Then we shift traffic to that new ASG. Then we destroy the old ASG. And lastly, we deploy across 3 availability zones in each region, and we rely on auto-scaling to help us keep balancing. Next feature that we rely upon is fleet management, or replacing unhealthy instances. It refers to the basic ASG guarantee to keep the capacity at desired level. If it drops below desired, ASG tops it off. If it goes above desired, ASG terminates those instances. It could be tied to health check, but instance doesn't have to be healthy or unhealthy. We can terminate it ourselves. So in case of Chaos Monkey, well, the whole premise of Chaos Monkey is somewhat controlled chaos. Chaos Monkey terminates instances at random at a certain schedule to make sure that we don't terminate too much. It was developed as a tool to ensure that our stack is resilient to the loss of any single instance. But it was made possible by that AWS guarantee of fleet management. And another use case, obviously, alerting. We run a pretty extensive suite of alerts, including both threshold-based and outlier detection alerts. If we notice that a particular instance has higher error rates, higher CPU utilization latency, or anything else, we can simply terminate it, and ASG would give us a fresh, brand new, healthy instance. Another feature that we use, Lifecycle Hooks. This refers to the ability to get notification and run some custom actions as the instance transitions through the lifecycle from pending to in-service to running, well, in-service running, then terminating and terminated. So this is an example of our regular termination sequence. At Netflix, we use application discovery. You can think of it as application-level DNS. When an instance comes up, it registers in this discovery service at a certain alias, and it becomes discoverable by any other instance within that region. So other instances can send traffic. When we terminate the instance, either by alerts or by ASG dynamic scaling, the instance deregisters itself from discovery. What we noticed is discovery has a certain propagation delay. And again, well, granted that we have hundreds of thousands of instances, that's understandable. So sometimes this propagation delay is a little bit longer than it takes, for instance, to terminate, which leads to the situations that some other instances within that region can attempt to send requests to the instance that was terminated already, which obviously leads to errors. How do we address it? We introduced the lifecycle hook on termination. Essentially, this allows us to implement quiescence. When we transition from in-service to terminating, lifecycle hook kicks in. We deregister our service from discovery, then wait a little bit, drain all the traffic, and then once everything is propagated, we continue with terminating it. And lastly, dynamic scaling. So we'll do a deeper dive on dynamic scaling. I just wanted to call something out. In my first slide, I mentioned that we have 250,000 reserved instances. So you may be wondering, why do we even need dynamic scaling? Because all our instances are reserved. We can provision everything statically and pretty much be done with it. Well, OK, let me make a case for why we need dynamic scaling. These two images look the same. They look identical. By the way, these are still frames from our original money heist. Anybody watched it? Yes, yes, awesome. OK, for those of you who didn't watch it, I couldn't resist it. A little spoiler. This is season 1, episode 1, and it only gets better after that. So, OK, back to the images. The difference is one of these images is captured from a stream at 680 kilobit per second, and another image from a stream at 250 kilobit per second. It's less than half of the original bit rate. We can compress our streams without perceived loss in quality so that we can deliver it to more devices over various network conditions. Running encoding and running encoding optimizations at the scale that we do obviously requires a lot of CPU, a lot of capacity. Where does it come from? Here, the bottom graph represents our use of capacity for a particular instance type, for a particular region. You can clearly see our daily patterns of peaks and troughs. At 7 p.m., a lot of people watch Netflix, and we need more capacity to support the streaming. At 3 a.m., less people watch Netflix, so auto-scaling releases that capacity. We don't need it anymore, but it's reserved, it's still ours, so we can repurpose it for encoding, and that's what the top graph represents. Encoding jobs run during off-peak hours, and we built a pipeline that harvests this capacity and reuses it for encoding. Other uses of dynamic scaling, recommendations. Again, we can tap into this off-peak capacity to generate better recommendations. Yet another benefit, Redblack deploys. So remember, Redblack deploys involves cloning an ASG. If we were provisioned for peak, we have to double up. Since we auto-scale and we deploy earlier in the morning when our ASG is less than half of their peak capacity, we can save some overhead for implementing Redblacks. And lastly, regional failover. We deploy in 3 regions. We built a system that allows us to evacuate any single region and serve traffic from the remaining 2 regions. Internal name Kong. Well, that's why you see the picture. So how does auto-scaling play into it? Well, imagine, say, between North Virginia and Ireland data centers, regions, we see roughly the same pattern of peaks and troughs, but the peaks are shifted by about 8 hours. So when there is peak time in North Virginia, we have plenty of spare capacity in Ireland. That's the capacity we're going to provision anyway for normal use. So to support this failover scenario, we don't need to provision every region at double capacity. we need to provision it only for the local peak. And that helps us with saving capacity, saving cost. OK, so hopefully I made the case that dynamic scaling is helpful, is beneficial. A little bit of theory. In a nutshell, dynamic scaling is a feedback loop. Managed ASG publishes metrics to CloudWatch, and the CloudWatch has an alarm, which essentially tells you when the metric breaches a certain threshold after a certain number of evaluation periods. When it happens, CloudWatch sends notification to the scaling policy, and then scaling policy takes an action and either adds or removes capacity. And that completes the feedback loop, and it repeats. Each of these components have tunables. Probably the most important ones are metric and the threshold. But there's a number of other parameters that allow you to fine-tune autoscaling behavior. There's three fundamental properties of autoscaling. One is delayed reaction. And this question comes up pretty often. And again, as any system with a feedback loop, delayed reaction is unavoidable. There's no system with feedback loop that doesn't have it. So target tracking does a pretty good job of minimizing this delayed reaction. And with predictive autoscaling, we can minimize it even further. But I wanted to call it out to make sure that you don't expect sub-second reaction time. Autoscaling is comprised of multiple policies. These policies fire individually and independently of each other. The result is overall result, combined result of all these policies firing. And lastly, just to echo what Anup mentioned, ASG is bound by min and max, and it only changes desired. It never touches min or max, and it always respects them. OK, setting up dynamic scaling involves these 4 steps. First of all, we need to pick the metric. Then we need to pick the target or the threshold, our scale-up threshold. Then it's advisable to understand the traffic patterns and make sure that our first 2 choices, the metric and the target, are still valid based on the traffic pattern that we observed. And lastly, it's time to set up policies. So let's go over these 4 steps in more details. I also wanted to call out, so the examples are mostly based on our mid-tier services. However, the concepts that we're discussing are applicable to a wide range of services, it's applicable to batch services, it's applicable to edge services as well. All right, what metric? This question comes up so often that I even made an XKCD-style comic. The guy on the right is me, and on the left is a service owner who comes to me and asks, what should I scale on? And the answer is, the metric must reflect how busy the instance is, and it must change proportionately with the number of instances in ASG. And that's kind of like the classic definition of the metric that you can use for scaling. So what I noticed is a lot of times service owners tell me a little bit more about their service and what it does and how important it is, and then repeat the same question. So to clarify it, I prepared this slide. You can think of metrics roughly falling into these 2 broad categories. It's throughput-like metrics and resource utilization-like metrics. Very easy to relate to this because that's how people assess work as well. You can think of it in terms of how much work I did, how many widgets I produced, or how many miles I ran. Or you can think of it in terms of how tired I am. Out of the box, we have request count per target. It's an example of ALB metric. It's a throughput per target. And of course, ASG publishes average CPU utilization that can be used for resource scaling based on resource utilization. Both approaches are good for autoscaling, for dynamic scaling. There are slight pros and cons. I personally really like throughput simply because it's so direct and so intuitive. You can easily do math on it. For example, if you have some projection of your expected traffic, you can divide it by the target, and that's your estimate of how many instances you need to support it. The slight cons of this approach is that usually, as we make changes to our software, throughput target tends to drift over time. On the other hand, CPU utilization doesn't have this problem because we can normalize our workload by CPU utilization. We can say, hey, run as hot as, say, 60% CPU utilization. If all of a sudden our requests getting heavier and consume more CPU, ASG would simply give us more capacity. And that's the beauty of it. It requires less adjustment. However, on the other hand, it's easier to slip in some performance regressions. So if inadvertently you pushed out code that is now heavier on CPU, ASG would scale up to accommodate it, and capacity and cost might increase. Autoscaling on multiple metrics is something that AWS fully supports. It can be set up. In our experience, we found out that scaling on multiple metrics makes it harder to reason about ASG behavior. It's also easier to get into situations when different metrics contradict each other. Remember that scaling policies are independent. So if you set up one scaling policy on one metric that tells you to scale up, and then you set up another scaling policy on some other metric that tells ASG to scale down, both of these policies can kick in at the same time, and ASG would start oscillating. It would start scaling up and down repeatedly. Our typical setup involves scaling up and scaling down on throughput and emergency scale up on CPU. We call it the hammer rule. We can set the CPU threshold relatively high. So if we have an influx in traffic, or if we have some other event that drives CPU to dangerously high levels, we drop the hammer. ASG scales up by a wide margin, say 50% or even higher than that, and we can survive this event. Alternatively, we can scale on CPU, and especially with target tracking, it works really well for mid-tier services. What is my target? That is probably the most influential decision you would make when setting up auto-scaling. There is no shortage of tools that allow you to load test your service and see how it behaves under load and determine that target. There's tools that can generate synthetic load. There's tools that can capture the traffic and replay it. There's plenty of them. So at Netflix, we adopted what we call squeeze testing. Essentially, it's a load testing with live production traffic. This is a rough diagram of how it works. Without going into all the nitty-gritty of this setup, since we're talking about mid-tier services, this traffic is entirely within our ecosystem. We are in full control of this traffic. It is possible for us to divert a portion of traffic that is destined to a particular ASG. And we can send this traffic to a separate ASG with a single instance that runs the same AMI. Essentially, it runs the same software. So, and we have a knob for controlling this throughput. And that is how we can derive our target. We can squeeze test it with a live production traffic in conditions close to what we have in production. And that gives us a more precise insights into what the target is. And since we're squeezing a single instance, not the whole ASG, it minimizes the blast radius in case we squeeze it so hard that the instance fails. And we do squeeze it so hard because understanding failures is very important. So I know nobody wants to think about failures. Nobody wants really to talk about failures either. But as a performance and reliability engineer, I have to deal with failures of all kinds pretty much every day. So here's an example. The service on the left exhibit more or less normal pattern. We see that as throughput, the blue area ramps up from roughly 90 to 180 requests per second. We'll also see CPU doubling up from about 40 to 80%, and we see latency growing as well. So this service essentially can absorb anywhere from 90 to 180 RPS without like any adverse effects. Okay, well, maybe latency. Now take a look at the service on the right. There is a very, very distinct inflection point. When we reach a certain threshold, when our throughput reaches a certain threshold, this service simply fails. So we see that our latency goes up by the order of 2 orders of magnitude. We see CPU going from a little bit over 40 to over 90%, and we see throughput dropping. So this service simply fails, okay? Just to make sure that the difference is clear. So these two pictures illustrate the difference. The service on the left keep going, the service on the right fails. Why is it important and how is it related to auto-scaling? If you operate the service on the left, the good service, then it comes down to a trade-off. It's a business decision. Do you have an SLA by latency or some other metric? Okay, let's say you want to run the service at 30 millisecond latency. Great, run it cooler, give it more capacity, and meet your SLA. If, on the other hand, you don't have SLA and it doesn't matter if your latency is 30 or 60 millisecond, okay, well, then you can run it hotter and save on cost. Okay, if you have the service on the right, the bad service, the service that breaks, you simply don't have this trade-off. You have to make sure you're nowhere close to that point where the service fails. So again, in my opinion, understanding failures is important. It's important to know how it fails so we can prepare better for it. Speaking of traffic patterns, here's an example from our typical mid-tier service, and we're comparing traffic patterns of Friday morning versus Saturday morning. You can see that the Saturday morning traffic ramp up is much, much steeper. So why is it important? Usually people think of auto-scaling, usually the question they ask is, will auto-scaling give me enough instances to sustain my peak? And usually the answer is yes, it will. It will give you instances up to your max ASG size. What we noticed, the peaks are not the most dangerous times. The most dangerous times are the early morning hours. ASGs are at their lowest setting, at their lowest size, and the traffic ramps up quickly. That puts strain on auto-scaling. Auto-scaling have to provision instances quickly to make sure we keep up with this curve of traffic. Another example along the same lines is mixing regular and batch traffic. This anti-pattern could bring you some trouble. In this example, we see that the batch service kicks in and starts sending over 30% more traffic to one of our ASGs. And it happens over the span of maybe a couple of minutes. So that puts a pretty significant strain on auto-scaling. So better not mix regular and batch traffic. And to summarize it, the rate of change is more important than the peak volume. You can think of it as velocity versus acceleration. And again, even in human terms, we cannot sense velocity, but we can sense acceleration. It's kind of the same here. So your peak, no matter how high it is, for as long as it doesn't change very rapidly, auto-scaling is okay. But very sudden changes, very sudden spikes and fluctuations in traffic can be dangerous. Okay, so at this point, we have our metric. we have our target, we understand the traffic patterns, and it's time to set up our policies. How hard could it be? Here's an example of a mid-tier service that scales on throughput. And the top graph represents an ASG size, the gray area, versus throughput, a pink line. You can see that even visually, the shapes roughly match up. It kind of intuitively makes sense because as the traffic grows, ASG have to scale up and have to have more instances to process all this traffic. Now, take a look at the bottom graph. The bottom graph represents an essence of how autoscaling works. The pink line is our average throughput per instance. That's the metric we scale on. Yellow line is our scale-up threshold, and blue line is scale-down threshold. See, there is a band. We introduce a band. When the metric goes above it, we scale up. When the metric goes below it, we scale down. And we can see as the traffic grows, we keep bumping up in our scale-up threshold. ASG scales up, and that drives the average throughput down. And then the traffic keeps growing, and then it repeats. We reach the peak. There's a brief equilibrium moment, and then it keeps going down. And then we start bumping up against our scale-down threshold. So again, the band. Some people prefer to think of it as a dead zone, because for as long as you're between scale up and scale down, for as long as your metric is between scale up and scale down, ASG takes no action. OK, well, so it sounds relatively simple. Let's see how we can set up, or more likely, how we manage what mistakes we made in our environment when setting this up. So this is an example of misconfiguration. I call it the no-rush scaling. You can see that even from the top graph, you can see that the pattern of traffic and the pattern of ASG size, they do not match up. And when we look at average throughput, we see that it drops way below scale-down threshold, which means we're wasting capacity. And sometimes it goes above our scale-up threshold, which means we're running dangerously hot. So what was the problem with this setup? And again, this is not a problem with autoscaling. It's a problem with how we set it up. The person who set it up set the scaling thresholds as an absolute number of instances and not a percentage. So when your ASG is at 300 or 400 instances, 5 instances versus 5%, it matters. So the ASG simply doesn't scale fast enough. To fix it, we had to increase scaling amounts, or we could have migrated to target tracking that takes care of it automatically. Another example, quite the opposite, I call it twitchy scaling. So the service owner was not sure, was a little bit afraid whether they get enough capacity or not. So what they did is they set up scale-ups at 100% of capacity. So the scaling policy says, for as long as my throughput is above 100 for 1 minute, give me 100% of capacity. And that's what we see happening. As soon as we reach our scale-up threshold, ASG doubles up. But then what happened? It drives our average throughput below our scale-down threshold. And ASG immediately starts scaling down. That's why we see the spikes. So it's basically unnecessary capacity churn. To remediate this problem, we have to reduce scale-up's amount and increase the number of evaluation periods for the scale-up. Alternatively, we could have simply migrated to target tracking. And this is my favorite example. Should I stay or should I go? So the story behind this example is that service owners detected a slight performance regression on Friday afternoon. So they have a choice. Push a fix going into weekend, which is very much against our best practices, or scale up to accommodate this performance regression, survive the weekend, and deal with it later on Monday. So they chose the later. that letter. Good choice. So what they did, it used to be that scale-up threshold was at 120, scale down at 100. So they simply reduced scale-up threshold and set it to 100. So see, there is no more yellow line. It's kind of hidden. So scale up and scale down became the same. There is no more band. There is no more dead zone. And that is why autoscaling cannot stabilize. It keeps oscillating up and down. Well, so the remedy is to move scale up and scale down threshold far enough apart. And again, if you're doing, if you have a step scaling setup, that's very important. Or just use target tracking that doesn't have any of these problems, and it takes care of it automatically. To echo what Anup said, target tracking, you can think of it as a thermostat. Set it and forget it, and it does the rest. If you're familiar with step scaling, you can also think of it as a step policy with automatic unlimited steps. It has all the benefits of step scaling, but it doesn't have the complexity of setting each individual step, threshold, scaling amount. And on the top of it, in addition, it also is sensitive to the rate of change. Remember that slide when we spoke about the rate of change and how important it is? So target tracking is sensitive to the rate of change. So when the metric changes slowly, it adds less capacity and saves cost. And when the metric is changing rapidly, it adds more capacity and saves us from trouble. Benefits of target tracking. Easy setup, in my opinion, would be, that alone would justify moving to target tracking, but it also adapts to traffic better and learns over time. And that helps us to bring the cost down and availability up. It's not a zero-sum game, not in this case. Innovations like target tracking can address both of them. And we rely on target tracking heavily for our mid-tier services. And lastly, whether you have 25 or 250,000 instances, autoscaling has features for everyone. We use it at Netflix. We rely on it extensively, and it allows us to focus more on our business use cases and think a little bit less about infrastructure. Thank you. There you go.
Thank you so much for your time. If you can take 10 seconds to provide us feedback, we'll greatly appreciate that. And I do have the Spot credits. If anyone wants to try Spot instances, more than happy to share this. And we will be around to answer any questions. Thank you.